Okay, this section is very short. It's an introduction to chemical equilibrium. The goals are to recognize that all chemical reactions are reversible and that reactions eventually reach a dynamic equilibrium. Recognize the difference between reactant-favored and product-favored reactions at equilibrium. So, here we go. Very short section. Equilibrium reactions. These are reversible reactions, and all reactions are reversible to some extent. Some are so little reversible that they seem like they're not. For those reactions that are quite reversible, what we tend to use are these arrows here. That means that the forward reaction could go either way. So we use this instead of this, 2 arrows instead of 1. So in this reaction, what's happening is that CH3COOH is turning into the acetate ion plus a hydrogen ion. But likewise, these two are coming together and making one of those. So this is happening all the time, okay? So here's some things you need to know at equilibrium. So when you have equilibrium, the amounts of reactants and products are constant. So this amount does not change. This amount does not change, and this amount does not change. The forward rate equals the reverse rate. So if one of these is coming apart in 1 second, one of each of these is coming together in that same second. So that the amount of these doesn't change and the amount of these doesn't change. They stay constant. Now, I said one of these per second and one of these coming together per second. Not all of them, just one, okay? Rarely are the amounts of reactants equal to the amounts of products. You could have 5 million of these and one of them coming apart per second to make this stuff. 5 million of these and 1 per second coming apart. You could have 1,000 of these and 1,000 of these, not 5 million, 1,000 and 1,000 of each, and one of each of them coming together to make one of those. And that's equilibrium. Because if you have one of each of these making one of those, and one of these making 2 of these, the total amount of this doesn't change, and the total amount of these do not change. So these amounts do not have to be equal, and they rarely are. They rarely are. However, equilibrium can favor the reactants or it can favor the products. If we have more product than reactant, we say it's product favored. If we have more reactant than product, it's called reactant favored. So that's what this is right here. So the amounts of each are constant. The rates are the same. The amounts do not have to be the same. And if there are more reactants at equilibrium than products, it's reactant favored. And if there are more products than reactants, it's called product favored. Let's take a look at a couple of problems here. Identify each of the statements as true or false. At equilibrium, the rates of the forward and reverse reactions are equal. This is true. When a reaction reaches equilibrium, the forward and reverse reactions cease. This is false. When equilibrium is reached, it just means that the rates are the same, which means they're both still happening. Chemical reactions always proceed towards equilibrium, and that is true. Now, we didn't talk about this in detail, but it turns out that when you have these rates that are different, so if we take a look at the rates, if the forward rate is fast and so here we're going to have the forward rate is fast and the reverse is slow. So I'm going to signify that by this. Do you see how the forward rate is fast and the reverse is slow? Okay. So if the forward rate is fast and we make this reactants and we make, or excuse me, products and this reactants, what's going to happen to the amount of products if the forward rate is fast? It will start to grow. Okay. What will happen to the amount of reactants as the forward is fast and the reverse is slow? Well, the reactants get used up. And eventually there's going to come a time when if there are fewer reactants, the rate is going to slow down. So here the reactant rate slows and it evens out, and the product rate is eventually going to slow and even out, or not slow, plateau. Okay? So these things naturally proceed towards equilibrium because what happens is that you eventually reach this the amount of product and the amount of reactant that will balance out. So they always proceed towards equilibrium. So here we have a problem. Equal amounts of two acids, HCl and HCO2H, are placed in aqueous solution. When equilibrium is achieved, the HCl has the greater conductivity. Which reaction is more product favored at equilibrium? So for this particular idea here, we need to understand what makes the solution conductive. And the answer is ions in solution. Ions are what conduct electricity. If you don't have ions, they don't conduct electricity. So these conduct electricity, H2O does not. So this is something that's kind of interesting. The reason they tell you to get out of the water when there's a thunderstorm is because lightning may strike the water and you could get electrocuted. And the reason for that is because water has a lot of dissolved ions in it. The water that you drink, swimming pool water, lake water, river water, ocean water. So lightning can spread through these things pretty well because it's conductive. If you were in distilled water, that would be the safest place of all because it has the fewest amount of ions. But still, it does have ions, so it's not completely safe. So here, what they're telling us here is that this solution has greater conductivity and this one has lower conductivity. And they're asking us which is more product favored at equilibrium. Well, if this has more conductivity, it also has more product at equilibrium because that would give it more ions. So the answer is the HCl reaction. Okay, so this problem is kind of a jump ahead of where we should be, but that's all right. Okay, that's the end of this section here. Thank you for listening. That was a short one, right? And we're done.